Good morning. My name is Bill Efcavitch. I'm Chief Scientific Officer and co-founder of Molecular Assemblies. We're a San Diego-based company, and this is scrolling by itself. All right. I'd like to we're a startup company. We opened our doors in January 2014, bootstrapping ourselves with NIH, NSF, SBIRs, and now have raised several $1 million in small seed investors, and we're trying to develop a next generation DNA synthesis technology. So all the extant suppliers of synthetic DNA in the world use a chemical process that was invented in 1981. I'll talk a little bit more about that. And there's been a lot of downcosting, automation, miniaturization, a lot of physics, but not much change to the fundamental process. We decided to create a company using a unique method of synthesizing de novo DNA using enzymes. So before FedEx became the largest supplier of synthetic oligonucleotides in the world, there was a company called Applied Biosystems that commercialized the phosphoramidite chemistry method, and it certainly has become a billion-dollar industry in supplying oligos, and it's based on a rather remarkable chemistry invented at University of Colorado. And the young man in the picture is showing the first development of a commercial DNA synthesizer. Phosphoramidite chemistry is wonderful. It's produced lots and lots of synthetic DNA, but it has certainly reached a plateau in its technology development. Although there's been miniaturization, inkjet delivery, et cetera, the chemistry is essentially the same that young man was using in 1983. So the problem is yield, decreasing yield. No one seems to really understand why the limitations of the phosphoramidite chemistry exist, but in fact, if you look at the chemistry cycle, there's a group of at least 4 different reactions that need to occur, each with very, very high yield. So it becomes really simple to say, if my overall sum of all of the chemistry steps is 99 point something, that's going to tell me how long of a synthetic oligonucleotide I can make. And in fact, in 1986, I synthesized 176 long DNA fragment, and in fact that's pretty much the state of the art. So in 30 years, it's certainly the quality, since that synthesis, it's a UV shadowing gel, has gotten much better, but the length has not really increased much. And in fact, there's been a slow improvement in the cost. The DNA is damaged molecules that almost obligatorily require error correction. We said the length, and not to mention the fact that it's all based on organic chemistry, and so there's hazardous waste generation, which is not really sustainable. So at Molecular Assemblies, we decided to approach the problem not from physics, not from miniaturization, not from automation, but to develop a brand new approach, and that is to use a rather remarkable enzyme called terminal deoxynucleotide transferase, which is the only constitutive template-independent polymerase. So what we're developing is essentially an enzymatic analogy of the chemical method. We don't use a copying process. We're trying to use de novo synthesis. And some of the hallmarks are that, and I'll show you later slides, TDT can make very, very long single-stranded DNA molecules. It's sustainable. We're going to be working with a completely aqueous environment, and more importantly, it's scalable. We're not going to be doing just femtomole scale synthesis. We think that this technology is scalable over a wide range of syntheses, both small and large, which we think is important not just for synthetic biology, but for the entire market. Why TDT? TDT is, as I said, remarkable enzyme. It's very promiscuous, so it'll accept a wide number of modified oligonucleotides. It can make thousands, tens of thousands long strands of homopolymers in solution. So the basic premise we have is that if one uses an aqueous-based synthesis in this enzyme, one theoretically could make very, very long polymers. Yesterday, a discussion with someone, what are the limits of phosphoramidite? Maybe it's the fact that we're growing DNA in acetonitrile, an anhydrous system. Let's grow DNA in an aqueous solution and see if we can make it very long. So TDT's properties are very well known. It's an available protein. What's our approach? Very simple. We're going to do this on a solid phase. We're going to use a reversible terminator with TDT, add one nucleotide and only one nucleotide, wash that out, remove the terminator, and just repeat that cycle. Again, because it's an aqueous-based chemistry, we should be able to make very, very long molecules. Now, most people, if you ask them how to approach this problem, they'd say, we'll block the 3' hydroxyl of the nucleotide. That's very well known, described. We decided to take a completely different approach and use what we call virtual terminators that are attached to the exocyclic amines. After we cleave off the terminator by using mild reducing agents, the scar eliminates, and we're actually leaving behind natural DNA at every step. And because we're not using the 3' hydroxyl, we can exert an exquisite degree of control over the modifications. We can, in fact, leave scars on if we want, and as it turns out, we think this could be a very useful synthetic tool for making highly modified nucleic acids for a wide variety of purposes. So again, although I realize that this conference is devoted to synthetic biology, we consider DNA to be the industrial polymer of the 21st century. We're not going to be producing suits made out of DNA, but we think that with our scalable technology, we could approach not just synthetic biology applications, but larger scale syntheses to feed things like CRISPR-Cas applications or the recently emerging immunotherapeutic cancer applications, precision diagnostics. So again, and even beyond biology, DNA memory, nanotechnology. These are fields that are being hindered by the expense of making rather long strands of DNA and highly modified DNAs, and we think our technology will be applicable there. Lastly, this is our team down in San Diego. Don't have a picture of our newest member. So we are still in development, and stay tuned. Hope to be back in the future to show you some data of what we're able to accomplish. And with that, I guess I'll finish a little bit early, take some heat off the other presenters, and take questions from the audience.
Hi, I was associated with some iGEM teams that played with this, and the kind of the hang-up was always the cost of the modified nucleotides, which was prohibitive. And also, when we were doing it, we were using heat to cleave the modification off, and then the enzyme, you didn't like the heat, so you ended up with that. So how are you surmounting those two problems?
Well, cost of a modified nucleotide is just simply related to the scale. So if you make something large enough scale, the only reason phosphoramidites are inexpensive is because they're made in very, very large scale. So it scales directly. Eventually that cost can tumble down. And yes, we're trying to use a minimal modification as we can. We're actually exploring both these exocyclic amine modifications and 3' block modifications. With reference to the heat removables, that's actually one of the reasons that we didn't pursue 3' blocked is because TDT will not accept any modifications at the 3' end. It's a very promiscuous enzyme. We can hang a barn on the bases, and the enzyme incorporates it every day of the week, but any modification at 3' end eliminates the use of the wild type protein. So we didn't want to engineer the protein, and we decided to go that way. So our molecules come off with mild reducing agents, and we can, as I said, we can either leave the scar on till the end or take it off with the mild application of heat. But no heat required. Yes.
So a big part of contribution to error rates in oligosynthesis that winds up in synthetic genes comes from reactions that don't go to completion. And whether you're doing it enzymatically or with organic chemistry, you still have to push a reaction to completion.
Absolutely.
I'm not sure I quite understand the rationale of thinking how those enzymes are going to do a better job of pushing that reaction to completion than the traditional chemical.
Well, in some respect, you're right. I mean, it's chemistry. It's just chemistry. We can mass drive TDT to essentially quantitative additions. Back to the this, I was having a discussion yesterday at lunch. What are the limitations to the phosphoramidite methodology? Is it the coupling reaction, or is it subsequent degradation of strands that are formed during the synthesis? I don't think that's been really well defined. But TDT has, I don't know, I don't think it has an equilibrium point. So we've been able to drive it with low micromolar concentrations of really heavily modified triphosphates to what looks like quantitative addition. This year we need to be implementing a sequencing-based assay to actually see how many nines that we're putting on that. I'm getting the N sign. He had his hand up first. I finished early.
Can you explain secondary structure effects and how they may decrease efficiency?
It's a good question. Yeah, because we're doing the synthesis in solution, we have to worry about secondary structure effects. As I mentioned, we can actually leave that scar on if we want. And so, we're thinking some minimalistic scar on the N3 of G or the N4 of C will banish secondary structure effects, we hope. Okay, we're done now.